Good day, everyone. On behalf of Cambridge Health Tech Institute's Global Web Symposia series and our sponsor, Wyatt Technology, I'd like to welcome you to Understanding Monoclonal Antibody Unfolding and Aggregation. My name is Elizabeth Lamb, and I'm the host and moderator for today's event. Now I'd like to introduce our presenter for today. He is Professor Wolfgang Fries, Professor of Pharmaceutics and Biopharmaceutics at Ludwig-Maximilians University. With that, I will turn the presenter ball over to Professor Fries. Welcome, Dr. Fries.
Thank you very much for the kind introduction, and also a warm welcome from my end. And I also want to thank Wyatt for hosting this webinar. It's about understanding of monoclonal antibody unfolding and aggregation and how DLS can help us with that respect. The outline of today's presentation, it's about the background on monoclonal antibody stability. It's about analysis of protein-protein interactions by dynamic light scattering, how to determine the KD by dynamic light scattering, temperature-dependent studies of this interaction parameter KD, the importance of KD for understanding interface-induced mAb aggregation, as well as the application of KD for understanding interactions of monoclonal antibody conjugates. As a background, some facts about current mAb formulation development. You see here some market products, and what is indicated is that the concentration of protein in this formulation is rather high. We've reached concentrations of roughly 150 and even higher gram per liter. And with that, we have to focus these high concentrations and stabilize them. Stability for mAbs means that we have to consider different aspects. And three major aspects are focused on the chemical stability. And you see here an example for deamidation that can occur. It's about a conformational stability, so the stability of the secondary and tertiary structure. And in addition, it's also about the colloidal stability, so the interactions of the protein molecules in solution. One factor contributing to all that is the reversible self-interaction, because it directly is related to the colloidal stability, meaning that this association and interaction can lead to formation of larger aggregates, more or less native-like. On the other hand, it's also linked to the conformational stability, because upon unfolding, hydrophobic parts of the protein become exposed. And if already initially the reversible self-interaction is pronounced interactive and attractive, this can be even enhanced if conformational stability or an unfolding event is added on top of this substantial interaction. On the other hand, if conformational instability occurs, unfolding occurs, if there is repulsive interaction, it may mean that although unfolding occurs, aggregation may not necessarily occur. In addition, this reversible self-interaction triggers also the extent of solubility of the protein in the solution, and it triggers one important problem, and that can be a viscosity increase at these high concentrations in the injectable formulations. So what happens if we increase the mAb concentration in the formulation substantially? Interactions also occur at low concentrations, but they become even more relevant at high concentrations, because also at that stage, the propensity and the probability of interaction is increased. And we have the so-called molecular crowding effect, means that we have excluded volume which is not accessible for each individual molecule anymore and restricts its mobility. We have pairwise, short-range and long-range intermolecular interactions, typically triggered by electrostatic and hydrophobic interactions. And we also have non-pairwise interactions and cluster formations, also triggered by the same phenomena. Now, how do we see these interactions? A non-pairwise interaction can be nicely studied by dynamic light scattering. In this study by MedImmune using DLS and static light scattering, it was tested that the antibody at 10 mg per ml in a 10 millimolar histidine buffer upon addition of salt substantially increases in the hydrodynamic diameter, which is not really correct. The antibody itself does not increase in the hydrodynamic diameter, but larger clusters form from the hydrodynamic diameter of the antibody of about 6 nanometers. You can envision that in the presence of salt, these must be large multimers if something is generated with a diameter of 16 to 20 nanometers. It is not necessarily related to the cation, as you see with the comparison of lithium serum and sodium, but the anion is more important, as you see with the effect of iodide and sulfate. What you see on the right upper corner is a comparison on the effect of pH. And interesting, what the authors concluded was that the interactions are pH dependent, as indicated by the citrate-phosphate buffer combination, as the hydrodynamic diameter increases from 10 at pH 5 to about 22 at pH 8. Considering histidine buffer, however, you can see that the hydrodynamic diameter hardly changes. As we had learned before, the anionic species are very important for the cluster formation of this protein. With citrate and phosphate negatively charged, these anions trigger this cluster formation, whereas histidine, as the positive buffer species, does not affect this. What you also see is the effect of hydrophobic interactions. In the left bottom panel, you see the hydrodynamic diameter upon addition of different amino acid. The amino acid, if you start with alanine, which is the top line, you see that the increase in the hydrodynamic diameter is much more pronounced as compared to the amino acids phenylalanine, tyrosine, and tryptophan. So the aromatic amino acids interfere with this hydrophobic interaction. And we can measure this by net dynamic light scattering. As the molecules move, we see the scattered light on the detector. We have these light intensity fluctuations. And from the autocorrelation analysis, we can analyze the diameter of the species. And this we can measure with about a change of about a radius of about 1%. So we have a rather sensitive method to look for this change in the hydrodynamic diameter. Here you can see an interesting molecular antibody behavior studied by size exclusion chromatography, dynamic light scattering, and asymmetric flow field flow fractionation. Many people start looking at the association of antibodies by using size exclusion chromatography. Studying 24 different formulations of different pH and sodium chloride, as you can see in the left upper panel, in the size exclusion chromatography, you don't get any change in the UV signal. It all looks like monomer, and you get the respective molecular weight by moles. However, when you do the dynamic light scattering study, you can see that in the absence of salt, 0 millimolar sodium chloride added, the pH has a strong effect on the hydrodynamic radius measured. At about a pH 7, you see that the radius is almost 20 nanometers. pH 5, it's down to 6 nanometers, as we would expect for the monomer. We can get to the similar range at the high pH end. But in between, we do see the cluster formation. The cluster formation is suppressed in the presence of 70 or 140 millimolar sodium chloride. And this effect you cannot see in size exclusion chromatography, because with the eluent having a higher salt content and the protein being diluted at the detector, you don't see any difference between the formulations. Now, AF4 is something strange. It's somewhat in between. So you see the size, which is indicated by the DLS. You also see, depending on the pH, a change in retention time. But when you look at the Maltz signal, you all see that it's almost the same Maltz signal for all the different formulations. So at the detector, we always see the monomer, but the retention of the sample is more related to the initial radius. So upon focusing and applying the sample in the AF4, we do see the retention, the size increase, but then dilution occurs, and we get sort of a mixed effect, and we don't see any effect at the detector end. Whereas we do see this substantial effect upon non-pairwise interactions. Pairwise interactions may be much harder to detect because we only have a slight effect in this formation or this interaction towards the tendency to at least behave like a dimer or like a larger, higher molecular weight species. And these intermolecular interactions become significant when molecules are proximal to each other. Proximal means when separation is of the same magnitude as the molecular dimension. So here we use the interaction parameter, the second virial coefficient, called B22 or A2. It is typically studied by membrane osmometry or by AUC or SAX, also by static light scattering. But it can also be very simple and straightforward to analyze this factor by dynamic light scattering. What really helps us with that respect is a plate reader system, because with the plate reader system, we can analyze much more samples at a much higher number of samples and replicates, because we require a concentration series of the molecule of interest. So with our microval plate reader, we can analyze 96, 384 or 1536 standard val plates. It covers a similar size range as a standard DLS. The sensitivity of a 14 kilodalton protein is about 0.125 mg per mil. Sensitivity is related to the molecular weight, so for an antibody, the sensitivity is actually much higher. We can use it for temperature-ramped studies, as I will explain later. We can use it also at dedicated temperature without using a ramp. And we can rather quickly scan an entire well plate. So the major benefits are that we're really fast and we only require small volumes. We can measure down to volumes as low as 5 microliters. And this facilitates the temperature ramps. It facilitates KD analysis, and that we can do more replicates. So how do we determine KD? We can derive KD from the slope of the apparent diffusion coefficient as a function of the protein concentration. In this example for a mAb, the concentration range is between 1 and 8 mg per mil with replicates, and you see the diffusion coefficient, and you can analyze the slope of this curve. In this case, positive slope, and we will later on see that we need to make some transfer to AD, to A2 and B22, that this is pointing towards net repulsive interactions. Same concentration range, same antibody, different formulation. You see that the slope is negative, and a negative slope points towards net attractive interactions. Now we can use this slope slash the KD and transfer it and compare it to the standard A2 values. In order to transfer that, we have to make corrections for the molecular weight, the friction coefficient, and the specific volume. A couple of years ago, there had been several studies, and they all came to a similar correlation between KD and A2. The first one by Lehammer you see in the left graph. Kd is related to A2 by the factor of 1.06, the molecular weight minus 8.9. So we have a slight offset, and this is what I just tried to explain, because if A2 is negative, it means that we have net attractive interactions. If it's positive, we have net repulsive interactions. Kd now has a slight offset, so it's not just simply that you can indicate and read everything just by the sign. Very similar equations were derived by Roberts, you see in the left bottom corner, and by ourselves, where we looked at various different antibodies and various different studies and tried to correlate the Kd with the A2 values and data presented there. Here you can see a typical effect of pH and ionic strength on this interaction parameter of a monoclonal antibody. You see the original curves on the left-hand side for histidine buffer, citrate buffer, and acetate buffer at different pH and in the presence of sodium chloride or arginine hydrochloride. In the table, you see the Kd values supported by the 95% upper limit and the 95% lower limit for the fit. So what you see is that the Kd at pH 6, the increase in ionic strength leads to an increase in Kd. It reduces the mAb interactions. At pH 5, there's no influence of the ionic strength observable. And the Kd values are higher than at pH 6. At pH 4, we have repulsive interactions. This is correlated to the charge on the protein molecule, meaning that at the lower pH, it's more positively charged and we have stronger repulsive interactions, and in this case then also almost net repulsive interactions. Kd is correlated in many cases to viscosity, not necessarily in all cases. There are literature cases and also from our own experience, cases where there is no correlation between Kd and viscosity. And this specifically holds true if the viscosity gets really high. In this study by Connolly, you see that they presented a correlation between Kd. If there's a Kd which is highly positive, strong repulsive interactions, the viscosity is low. And with a decrease of Kd towards the negative values and into the negatives, you see that the concentration leads to a high viscosity for these monoclonal antibodies. So Kd can be used as the parameter to study antibodies and to understand their behavior at high concentration and the viscosity built up at high concentration, although you do the studies at low concentrations. As said, the plate reader is very helpful in supporting temperature-dependent studies. A typical simple outcome you can see here. The red line shows you the Kd, so that's measured at room temperature. What you also see is the temperature of aggregation, and it's the onset of that, meaning that unfolding starts, and what you see is that already at higher repulsion, when the high Kd is higher, also this temperature at which aggregation starts is higher because we come out initially from more repulsive interactions. We have a lower Kd, we heat up our monoclonal antibodies, they start to unfold, and the propensity to form aggregate is higher, so Tag is lower. Overall, this is just one mAb in 22 different formulations. Now expanding on this, with this temperature-dependent studies, DLS can become a complementary method beyond colloidal stability study to typical temperature ramp methods like DSC or DSF. It can also be supported by temperature ramped UV-Vis, fluorescence, or IR study. Because what happens with our antibody molecules is that we measure TMs, 50% of unfolding based on DSC as defined. But if we do a formulation study, we want to understand what are destabilizing conditions and what are stabilizing conditions. And under these conditions, TM should be changed to higher or lower. Here you can see this exemplarily for cetuximab. When we ramp cetuximab up at 4 mg per ml in histidine buffer pH 7.2 in DSC, we can see two transitions which are related to the Fab and the Fc part. If we do the same with DSF, with an extrinsic fluorescent dye, we see the unfolding of the molecule, the dye interacting with the unfolded state, which is rather sensitive. And then, after unfolding of this first hydrophobic part and exposure of these hydrophobic parts, the secondary increase in the second peak we can still detect, but not with the same sensitivity. So there's sort of a, let's call it a saturation with dye already. Comparing this and doing this at pH 5 on the right-hand side, you see in DSC that we see three different transitions, which are still related to the Fab and Fc part. And you also see a similar trend and effect in the DSF. So overall, these DSF and DSC traces, let's say, correspond. They're not the same. They not just go by the energy, the DSC, and the exposure of the hydrophobic sites, DSF. It is something different. And when we look at the TM of DSF, the values are systematically lower than those from DSC. When you do a more detailed DSC analysis and generate the Fab and the Fc part of the antibody separately, you can learn more about the molecule. Just looking at the Fab trace itself, you see that the Fab unfolds at well above 70-75 degrees C, and even almost without unfolding, you see the yellow dot indicating the aggregation. So the Fab part, as soon as it tends to unfold, it starts to aggregate already. And that's different from the Fc part, because you see that the Fc part shows two different transitions. So the first part of unfolding already starts at temperatures well below 70 degrees C, but without leading to aggregation. Aggregation sets in at about 75 degrees C before, or maybe in the case when the second unfolding starts to occur. When we look at the overlap of this curve and compare it to the full map and just doing the calculations and comparing the curves, we see that there's a perfect overlay between the full map and the fragments. Now, when we do this in presence of sodium chloride on the right-hand side, we see basically a similar picture. The Fab part already aggregates almost when it starts unfolding. Fc is about the same behavior as in absence of salt. And also there's a very good overlay between the theoretical, the calculated solutions as the mixes of the different fragments, as well as the full monoclonal antibody. Now let's have a look at the same behavior and the molecule at pH 5. So left-hand side without sodium chloride. And we see and we know that the transitions are shifted to lower temperatures. At the same time, at pH 5, also what we see for the other molecules is that at a lower pH is the repulsive interactions are more pronounced. Now in the left chart, you see that the Fc part already starts to unfold much earlier. you can also see that the Fab part almost hardly changed in its transition temperature compared to the higher pH that we saw before. Now we also have more of a mismatch between the solution mix of Fab and Fc, and even more pronounced so for the full mAb. And what we also notice is that we don't have aggregation at all anymore, neither for the fragments nor for the full mAb. Now, in the presence of salt on the right-hand side, we have charge shielding, and these repulsive charge interactions are reduced. So now again, aggregation sets in. We can see that very clearly for the Fab and the Fc part. Now Fab has to unfold maybe a little bit more pronounced. Fc has to go through the first transition going into the second transition. And again, there's a mismatch between the combination and the full mAb behavior. So the higher Tm values of the full mAb even suggest sort of a mutual stabilization. And now we combine that with the dynamic light scattering studies. This is the DLS well-played ramp study for the cetuximab at pH 7.2. You see that the hydrodynamic diameter goes up substantially as the temperature increases, as you would expect. The hydrodynamic radius stays the same, and also the interaction parameter Kd does not change for a long time, up to about 60 degrees C. And this is when unfolding sets in. And with this unfolding, you can see that we reach the Tm of the CH2 domain. This leads to a substantial change in the diffusion coefficient, meaning that we all of a sudden have larger species, that we also have a strong decrease in Kd, meaning that we have substantial interactions between the molecules. And this happens even before we see noticeable precipitation. We have to be careful with this Kd though at this stage. I would only call it an apparent Kd because the species change and there's also the size increase, so we should not take that as 100% a correct value. Now when we look at the Fc part only at pH 7.2, we see a similar behavior. However, although we run more into the unfolding as we have seen in the DSC experiments, there's still an increase in the hydrodynamic radius slightly at the end of the 60 degrees. The diffusion coefficient still increases from 50 close to 60, 65 degrees C. So unfolding sets in. The hydrodynamic diameter increases with unfolding. The interaction parameter decreases. And that all happens substantially before the precipitation effect sets in for the Fc part. For the Fab part, we had noticed in DSC that the aggregation occurs almost at the beginning of any unfolding event. And this is also what we noticed in the DLS experiments. We could only get reasonable results up to a temperature of about 55 degrees C. At the next point, at 60 degrees C, it was all precipitated and we could not get substantial and realistic data anymore. Here comes the same sequence of mAb, Fc, and Fab at the lower pH of 5. At this pH, we have a higher Kd, as you may see. We had about 0 before, now it's about 40. So we have stronger repulsion. As we come into the unfolding region, still the diffusion coefficient increases, RH only slightly increases with the unfolding, and also KD decreases, so hydrophobic patches become exposed. However, we don't see this substantial precipitation, this substantial decrease in the interaction parameter, and we can also follow this slight unfolding event. Although we don't notice precipitation, we see that we have associates formed at temperatures higher than 80 degrees C. At the low pH, we had seen that the FC part unfolds much earlier. And this is also what we notice in the DLS experiments. Although the hydrodynamic radius stays still in the same region, at about 50-55 degrees C, we see that the KD starts to decrease. So we go into the unfolding and we see the substantial formation of attractive interaction, and this becomes even more pronounced at the higher temperatures, stronger interactions, although we don't see the formation of these large visible aggregates, but we certainly have the formation of larger clusters, just based on the FC part. The part which was much more prone for aggregation was the Fab part. For the Fab part, as soon as unfolding sets in, we have a substantial increase in RH, so we have substantial cluster formation. But when we look at the KD, we see that already at 50, 55, 60 degrees C, the KD starts to decrease. So already at that temperature, far before our unfolding occurs, we must see change in the Fab part that lead to a much stronger attractive interaction. So in summary, at pH 5, overall the conformational stability of monoclonal antibody is reduced, as we see based on the lower Tm values. We have electrostatic repulsion, and the KDs are above 0 mil per gram. And that prevents aggregation of the full mAb, the FC, and the Fab part. Certainly, the attractive interactions of mAb, FC, and Fab increase upon unfolding. The attractive interactions of Fab already set in well below the Tm onset. At the higher pH, without or with salt, and also at the lower pH with salt, we have higher conformational stability. The neutral net charge and shielding effect of the salt are important. The full mAb and the FC, the thermal unfolding is triggering the aggregation. And the newly exposed hydrophobic patches mediate a reduction of KD. Fab, the precipitation at elevated temperatures already occurs well below the Tm onset again. So we have to balance out. We have a reduced conformational stability at pH 5, but we have a reduced interaction. So if we stay well below this temperature, aggregation may be less of a problem if colloidal stability is the critical pathway of instability. At the higher pH, the conformational stability is increased. However, also the aggregation propensity is increased. And also here, long-term stability studies have to show which is the critical pathway. I showed you before this molecule with the interesting behavior and this reversible self-interaction studied by AF4, SEC, and DLS. Here an additional study on this very molecule, a temperature ramp study, to show you a different behavior. The green lines show you the temperature profile, and it's repeatedly warmed up from 25 to about 45 degrees C, cooled down again, reheated. The black crosses indicate the molecular weight. and you see the initial clusters of about 6 mers that form at room temperature, which then fall apart with increasing temperature, reform when we cool it down, and dissociate again when we ramp it up for several times. This has actually been a study with the static light scattering system, the nanostar. Now, two additional aspects beyond the temperature-dependent behavior of a monoclonal antibody. One was on the behavior of an aggregation of protein at the interface. Upon mechanical stress, shaking, stirring, pumping, we know that large aggregates can form. And this is affected by the formulation. And there's a hypothesis that these protein-protein interactions are important for the state and the formation of these aggregates upon mechanical stress. There had been a study by He et al., and they saw that with a higher KD, the particle formation upon mechanical stress in formulation of one mAb was substantially reduced, whereas if the KD was at 0, or let's maybe call it low, we had substantial particle formation. There's not, let's say, a real line of correlation into that, but it really tells you that the repulsive interaction may lead to the fact that upon mechanical stress, we have less aggregation. So we studied that. We used the mAb, placed it in the Langmuir trough, and we did infrared spectroscopy at the interface. What you see on the left-hand side is the IR signal, and at the low surface pressure of 5 millinewton per meter, you see slightly or faint bands in the amide 1 and 2 region of the antibody. And you also see a substantial OH band, which is related to the water molecules for the reference trough. When we compress it, we can get even more refined signals. So we move the barriers of the Langmuir trough. You really see that there's a film formation at the interface, and you can notice that and appreciate it in the pictures on the left bottom corner. We evaluated the IR spectra, and they're very similar to what we see in solution, and we cannot really tell whether the protein is unfolded or not. In addition, what we did is we checked the pH effect, and we don't see a pH effect on the IR spectra. We also did not see a clear effect on the right-hand side, as you see in Brewster angle microscopy, which enables you to see changes in the film at the surface at a, let's say, larger level. We see these clusters of protein, and this is all within a film, so you could even compare it to the Arctic Sea, where you may have some ice shields and floats on a different ice shield, so it's all overlap within a protein film. When you do AFM studies, you see also that there is some aggregate or cluster formation when you compress the film and then decompress the film, as if these larger structures formed can dive away. When we look at the mAb and shake the mAb, we see that with increasing pH from pH 2 to 9 for mAb 1, we get a stronger particle formation. When we look on the right-hand side of the right red graph, we see that the KD value of the mAbs of this mAb is overall positive and decreases with increasing pH. So the lower KD reflects the higher particle formation. Now comparing this to a second mAb, we see that the second mAb has a lower KD, so it should have a higher propensity for particle formation because it's stronger attractive interaction. And it's actually a mAb which almost falls out of solution at about a pH of 7. So when we study this mAb at a lower pH, between pH 2 and pH 6, we see that the particle formation is much more pronounced. You see that we have 40 to 50,000 particles at pH 2 for mAb 2, compared to less than 10,000 for MAb1. And again, a substantial increase with increasing pH. Comparing that to a third, a polyclonal IgG, so again, an apparent B2 value which we should refer to, the B2 values are even lower. So we start out with even stronger particle formation. And then in the end, also at the high pH, you see that we have particle formation up to 500,000. So we have this correlation between the KD value that we can measure and the propensity to aggregate formation at the interface. One last study was on mAb-conjugates and to study and use the A2 as a function of temperature to understand the behavior. This slide is rather busy, but I just want to point out a few small highlights. So we see the mAb, cetuximab again, at different temperatures, and we see that, for example, in histidine with H, in the presence of sucrose, S at pH 6.5, with ramping up the temperature, KD decreases. When we look at the middle, we see, for example, phosphate with sucrose pH 7.2. We have much more attractive interactions to start with, and upon unfolding, it becomes more and more difficult to really tell a difference. Now, when we introduce a conjugate, and the conjugates are typically hydrophobic, what you see is for DEAC, a hydrophobic dye, that overall the KD values are lower and that the KD values become decreased. So overall, we see that as soon as we introduce an additional hydrophobic moiety, the attractive forces become more pronounced. This changes, however, for the mAb fluorescein, because there we introduce a hydrophobic moiety, and as in addition, we change the charge. So you see that the isoelectric point of these molecules are changed. Now with that, if we study at pH 6.5, already at room temperature, we have substantial attractive interactions at the lower pH, meaning that at this stage, we have much more and stronger attractive interactions if we introduce this moiety and also change the charge. Whereas you can see there's one area of positive A2 values, and that's in phosphate buffer with sodium chloride, pH 6.5. And this is now surprising that we see this substantial increase because for quite a number of species, we must be above the isoelectric point, leading to repulsive interactions. So the KD analysis helps us to understand and predict the behavior of conjugates as well. In summary, the DLS measurements and the A2 measurements in mAb formulations, they provide us with information on protein-protein interactions at the storage conditions. The A2 can actually be a missing link in temperature and interface-induced mAb aggregation. For this, we need the plate reader, which enables us a fast A2 analysis and also temperature ramps. I want to thank you for your attention. I want to thank Wyatt Technology for hosting this webinar and for support. I also want to thank all the members of our team. Specifically, I presented you studies from Tim's work, Corinna's work, Alan, Martin, and Lorenzo. And I also want to thank all of our collaborators, also financial supporters, and thank you for your attention. I'm looking forward to your questions.
Thank you very much, Professor Fries. We do have several questions for you. Our first one is, what is the information for TAG coming from?
The information for TAG was derived from UV measurements in a regular UV meter and a cuvette-based system. So completely different than what we use for the DLS measurements in an independent method.
Okay, got it. We have a question specific to one of your slides. On slide 15, the diffusion coefficient converges to one value at 0 concentrations. My experience is that when I measure diffusion coefficients as a function of protein concentration in different formulations, I rarely get nice curves where all converge to the same diffusion coefficient. How do you interpret the data if you get different diffusion coefficients when extrapolating to C equals 0?
Yeah, this is really difficult because we also experience this in quite some cases. What you can do is that we do a couple of repeats. We really check our concentration determination method, and one can notice that especially if the measurements at the higher concentrations are somewhat off, they are more affecting the slope of the whole system. So I would say that especially repeats at the higher concentration may be helpful. But we also see this phenomenon. These were, let's say, really very nice data and a nice set of data and for a very, let me call it, clean and controlled measurement at mAb.
In some of the measurements of DLS versus temperature, there seems to be a lot of change going on in RH and KD 10 or 20 degrees below TM, while in others, these changes occur in the vicinity of TM. How would you explain these differences in behavior?
Our interpretation of this phenomenon is that when unfolding starts, it may not necessarily be that we have a, let's say, bigger part of the protein unfolding and a part which is maybe charged or hydrophobicity based, highly responsible for the interactions. We tend to look also at the onset of these transitions, because if we see that already at a temperature further below the TM, we see a change in especially KD or RH, then it's something which could be, let's say, considered as more critical, for example, for an interaction or for a formulation than if it does not occur at such a low temperature. One also has to consider that though the temperature ramps are different in the DSC or in the DSF measurements, we have temperature ramps of about at least 1 degree C per minute. In the DLS system, we typically have a lower rate because we need some acquisition time. And specifically, if we also go for the KD measurements, where we need replicates and multiple concentrations, we use a slower ramp. So the changes that we notice can, just based on the ramp rate, also occur at lower temperatures already.
Excellent. Our next question, what, in your opinion, are the relative values to the formulator of melting temperature from DSC, melting temperature from DSF, DLS onset temperature, aggregation onset temperature from SLS, and the KD temperature onset point?
Well, we like to look at the combination of all these different parameters, that we know if something, for example, is stored at certainly a temperature which is maybe quite some degrees lower than the TM, and it has a strong attractive interactions and a tendency to form aggregates, this may be actually more critical than, for example, a lower TM but a low propensity for aggregate formation. So it is the combination, and it also has to be, I think, correlated to the critical pathway of stability which a formulator typically has to look at. I called it these 3 C's. And we may optimize for an ideal TM, which is, let's say, far above what we would ever expect that something could happen, and would not consider that this pH is just simply critical, for example, a chemical instability like a deamidation.
All right. We have time for just one more question. Can DLS discriminate between reversible and irreversible interactions?
I would say yes, because for maybe referring back to this example that was comparing the SEC, the AF4, and the dynamic light scattering data, you can manipulate the sample in a way, or change, dilute, bring the pH, add some salt to increase the ionic strength, and you don't have a further manipulation of the sample like in SEC, where you have to mix it with the eluent. So I would say yes, you can discriminate between reversible and irreversible if you come up with, say, an experimental setting where you can challenge the reversibility of the interaction.
All right, perfect. Thank you so much, Professor Fries. I'd like to thank the folks at Wyatt Technology for sponsoring today's web symposium. Also, there were several questions we didn't have time for. I am forwarding those along to the folks at Wyatt and to Professor Fries, so you can expect your answers via email. Most of all, I'd like to thank those of you who came and spent this time with us. I hope you found some information that will make life a bit easier for you. Thank you again so much for attending. Have a great day.